Hi, it's Mr. Anderson, and this is Chemistry Essentials video 10. It's on light and matter. Matter is what we're made of, but I've got some matter on the screen and you can't see it because there's no light. Once I add light, we start to see matter. And so we can see solid, liquid, gas, and plasma. And so until we have light, we really can't probe matter and figure out what it's made up of. And so in this video, I'm going to talk about light and matter. Remember, light travels in these little packets called photons, and we can quantify its light using Planck's equation, where energy is equal to h nu, and h is going to be Planck's constant, and nu is going to be the frequency of the light. But we can use these little photons to probe matter and figure out what it is, because if you have a molecule and it absorbs a photon, it absorbs a certain amount of that energy. And when it releases a photon, it releases some of that energy as well. And so we can use different types of photons to figure out different things about molecules. And so infrared light is incredibly important at looking at the vibrations within atoms and molecules and figuring out what bonds they have. If we're using ultraviolet or visible light, we can look at the electronic structure. In other words, where the electrons are found, the outer electrons, and what they're doing. And then finally, we can look at solutions using light. And as we shine light through a solution, some of that light is going to be absorbed. And so we can figure out, according to Beer-Lambert law, what is the concentration of those absorbing molecules. And so light, remember, is a wave and a particle. And so if we're looking at it as a wave, we have what's called the electromagnetic spectrum, all the way from radio waves to gamma rays. Radio waves are going to have a really long wavelength and a low frequency. That's how many waves we have per second. Gamma rays are going to have really high frequency, small wavelength. And we're just seeing a small portion of that. When you look at me, you're only seeing visible light. And so light is a wave. Light is also, however, a particle. And what that means is it's quantized, or it comes in these small little quantities. And so you can think of it like this. And let me play some music in the background. This is Rachmaninoff for violin and piano. Vocalize. And so a violin can play any note. You just move your finger up just in incremental amounts, and you can get any note. But a piano is going to be quantized. You're going to have specific quantities. You can only hit a C or a D or an E. And so really, which is light? Light is like a piano. It comes in these small little quantities of photons. And so we can measure that energy using Planck's equation, where h times nu is going to be Planck's constant times the frequency of the light. And so which of these wavelengths are going to have the highest amount of energy? Ones with the highest frequency, and those are going to be the gamma rays right up here. Which ones are going to have really low energy? Those are going to be the radio waves down at the bottom. And so what we can do is we can measure photons and how they're picked up by atoms, and it tells us a lot about what the electrons are doing. And so a spectroscope allows us to see this whole electromagnetic spectrum. One of the first scientists to do this was Newton. If you wanted to build one of your own, all you would need is a prism and then a small slit. So we run light through it, and it's going to split that light into the different colors that we could see. And so this would be a compact fluorescent, and you can see the different colors of light that are coming from it. In a typical chemistry class, you'll just use a cheap spectroscope like this. It's going to have a slit on one side, and then it's going to have diffraction grating on the other side, and then an eyepiece down here. And so when you look at a light, it's going to look like this. But if we were to look at an incandescent light, it's going to look different. We can look at different atoms, and it tells us a lot about their electrons. And so a spectrometer is simply a sophisticated spectroscope. What you're going to have is a source. So we're going to have some light on one side. We're then going to have a grating, and the detector now is going to be a camera. It's just like a digital camera that's picking up more of the light that we can't see. And what you do is you take your sample and then you slide it in like that. And so different spectrometers are going to allow us to see different things. And so in IR spectroscopy, what we're looking at is infrared light. And so what's interesting about atoms is that they're vibrating constantly. There's going to be a vibration between atoms and between molecules as well. And so let me give you some example. This would be a carbon and two hydrogens. And what they have are called degrees of freedom. And so there's going to be a lot of vibration going on within a molecule. And what you can have happen is that when you introduce infrared light, it can actually pick up some of that energy. The bond's going to pick up some of the energy of that infrared light, and it's going to make these vibrate even more. It's kind of like pushing somebody on a swing. If you keep pushing them at the right rate, eventually they go higher and higher and higher. And so what happens to that infrared light? It's absorbed. And so what we can do is we can use an IR spectroscope, and we can look at what frequencies of light are being absorbed, and then we can use a fingerprint or a correlation like this, and it's going to tell us what kind of bonds we're going to find within that molecule. Now, if we wanted to look at more of the electronic structure, then we'd be using UV or visible light. And so what we're doing here, same kind of a thing, spectroscope, where we have light, we have a detector, and this time we're just using UV light or visible light. And what we'll find is instead of vibrating those molecules, what we're figuring out is that the photons are being absorbed by electrons. They're moving up to a higher energy level. And so that's where the energy is going. And so we can use a spectrum like this, and it's going to tell us more what those valence electrons or the electrons on the outside are doing. And then we finally have Beer-Lambert law. And what that is, here's an example right here. We have a dye, and then we're shining a green laser into it. And what we're finding is that laser light isn't making it all the way through. And that's because we have molecules on the inside that are absorbing some of that light. And so here's an application of that. It's just a simulation from PHET. We have a light on this side, and then what we're going to do is we're going to measure the amount of light that's moving through it. So I've turned the light on, and we're going to set that to absorbance. It's the amount of light that gets through, and we're dealing with cobalt chloride. And so what we've got is a solution. You can see as I turn down the concentration, more light goes through, and as I increase the concentration, less light is making its way through. And so this is Beer-Lambert law. Basically, as I increase the concentration, less light makes its way through. And so I can do a quick little experiment here. I could set it at 0, and now at 50, and now at 100. Look what happens as we increase it to now 150. Look what's happening to the absorbance. More of it is being absorbed. Now let's move it to 250. And so here's my data right here, where on the left I have the concentration, on the right I have the absorbance. And you can see it looks like a pretty linear relationship. Let's graph it. So that's perfect. And so what we're finding is as we increase the concentration of the solution, more of that light is being absorbed. And so what you could now use is you could just take a sample, we could measure the absorbance of it, and then we could figure out specifically what is the concentration of that solution. And so what did we learn? That light, and using Planck's equation, travels in these little photons, and we could quantify that. We can use it to probe matter, and that's because molecules are picking up or letting go of these photons. And then remember the three major things. Infrared light allows us to look at the vibrations of molecules and tells us a lot about what their bonds are. Ultraviolet and visible light tell us more about their electronic structure, where the electrons are. And then in solutions, those absorbing materials, remember, will pick up some of that light, and so we can use Beer-Lambert's law to make predictions on the concentration based on the absorbance level. So you should have learned to choose the correct spectroscopy to measure vibrational or electronic motion of molecules. So again, if you're looking at vibrational, you better choose infrared, and if we're looking at electronic structure, then you should choose UV or visible light. And then finally, we could use the absorption of light to determine the concentration of absorbing species in a solution. That's Beer-Lambert law. As we increase the concentration, we increase absorbance, and I hope that was helpful.